All right, so we're going to finish talking about sound and sort of the characteristics of sound, and then we're going to move on to talk about how sound is transduced into neural energy. So how do we get from sound to sound, right? So what are the two definitions of sound that we talked about last time? Right, sensation and perception, essentially, right? So there's the physical stimulus, the pressure differences, sound waves that are the physical stimulus, and then there's also the psychological perception of sound. So we're going to talk about sort of the interface between the two today. So how do we go from the physical stimulus to our perception of sound? But first, we need to finish talking about the physical stimulus. So what is timbre? And what are the characteristics of complex tones, and how do these characteristics determine timbre? Why is it not pronounced timbre like it looks? Yeah, it's the quality of sound. So quality how?
Like a different, I don't really know how to describe it. Like the saxophone makes a different sort of sound than a flute.
Right, exactly. So you can play the same note, the same tone on a saxophone and a flute, and they're going to sound different, right? You're able to pick out the saxophone from the flute. Do I have examples? I never know when the sounds are actually going to come up on this because there's no visual cue to these things. All right, so yeah, so it has to do with the sound quality. So sound quality is basically everything except for the loudness and the pitch. So everything else is going to constitute timbre. Timbre is created partially by the multiple frequencies that make up complex tones. So you've got several different harmonics. And we talked last time about different keys on the keyboard. So if you're going to play a low A, a middle A, a high A, then they're going to be multiples of the same frequency. So they're going to be doubling the frequency. So the fundamental frequency is the first harmonic. So that's the lowest common denominator, basically, for all of these frequencies. And then the additional harmonics on top of that are going to be the multiples of that frequency. So musical tones have additional harmonics that are multiples of the fundamental frequency, like I just said. Wasn't expecting that. All right, so let's listen to it again. Let me set it up. I should actually just put like a sentence on here. The tone that's coming up is, so it's a series of tones. We're going to start with a fundamental frequency, I think of like 200 hertz or something like that. And then we're going to add multiples on top of that every time. So the same fundamental frequency is still there. See if you can still pick out the low tone. But on top of that, we're going to add multiples of that. We're going to add other harmonics. So there's the fundamental frequency, the first harmonic. And there's two. So you could still hear the low tone, right? So that was still present. And the high tones just kept adding on top of that. So the waveform becoming more and more complex. So what we could do with something like that is we could break it down and we can look and see, okay, what is the amplitude at these different frequencies? So we take this complex waveform, do a Fourier transformation, do a Fourier analysis, and figure out what are the constituent sine waves. Then we can map out what is the amplitude of those different sine waves. So we have the frequency going up and different amplitudes at different frequencies. So if we were to look at a note played by a guitar, a bassoon, and a saxophone, so the fundamental frequency is still the same for all of them. So notice that the fundamental frequency is here at about 2 hertz. This is a long scale. Yeah, I guess it's 2 hertz. So they're all the same, and then the multiples of that, so the harmonics, are all lining up, but the amplitudes are different. Plus you get other sort of partials that are going on up here that are not present in the other ones. So a guitar is going to sound different than a bassoon, different than an alto saxophone, And the reason that they're different is because of the different frequencies that are present in this complex waveform. So this is what's comprising timbre. So timbre is what else is in there. So you've got the fundamental frequencies, but what else is going on? What else determines the sound quality here? So we've talked about this a bit, and there's a lot of text on this slide. Sorry about that. So just like with light, natural sounds never are made up of a single frequency or wavelength with light, but rather a complex set of them at different amplitudes. This is what makes an oboe sound different from the piano, even when they're playing the same note. So the fundamental frequency is the one with the lowest frequency of all the frequencies present, and this in part determines the pitch or the note of a musical instrument. So higher frequency elements of sound are called overtones or partials. Partials whose frequency is a whole integer multiple of the fundamental frequency are called harmonics. Together, the partials that make up a sound are referred to as its frequency spectrum, like we just saw, which in part is responsible for a sound's, for an instrument's timbre, or a sound's timbre. So, I'm going to play you 3 pianos. The same piece played on 3 different pianos, or 3 synthesized versions of 3 different pianos, actually. So, tell me which one you like the best. I'm not going to tell you what the pianos are or how expensive they are. All right, so here's the first one. Can you hear the difference? All right, and then finally. Which one did you like? Number 1? Christina says number 1's the cheapest. How come?
It sounds like it.
All right, so if we go back, let's see if we can hear the number 1 again. Okay, so a lot of people don't like it. So right there, there's lots of sort of high notes going on in there, or high frequencies going on in there. So somebody said it sounded tinny. Sounds sort of, or another description might be kind of bright and raspy. So that was a Yamaha. And it sort of has all of these non-harmonic partials going on. So things that are not part of the harmony, or not multiples of the fundamental frequency, that are sort of coming along for the ride, right? That they're extra frequencies that you don't really want. This one, the Baldwin, has fewer of those, so it doesn't sound quite so tinny, quite so bright. But contrast that one with the Steinway. So not a lot of extra stuff going on in the high end, right? So it's all multiples of that fundamental frequency. It's all harmonics. Ariel?
Any stringed instrument depends on which frequencies of sound are coming out of the strings, and some pianos have multiples in different, making up a single note with multiple strings. And so some of those high notes are up to 3 or 4 different. Is that correct?
Thomas?
I was talking to a piano tutor about a month ago at work, and he was saying that it depends on a lot of things: the shape of the piano, the type of material it's made out of, the quality of the material it's made out of, the structure of the hammers. There's a ton of different factors. He said like the piano tuners in Europe, they tune for like the
Wow.
So each piano sounds different because of craftsmanship, quality.
Yeah, so lots, I guess, is the answer to the question. Good musical instruments. So the musical instruments that you hear about, like the famous ones, the really expensive violins. What are they called? The Stradivariuses. They control basically the amount of sort of partials that are going on. So the things that you don't really want in the sound. This is sort of an aside. Has anybody ever heard of this? Binaural beats? Weren't we talking about this, Josh?
I think we were.
Yeah. So what's the idea with binaural beats? Do you know?
Yeah, it's called entrainment. It's trying to train your brain to get your brain waves pulsing at a certain alpha, beta, gamma rhythm. And what it does is you'll play two different tones into each ear. You have to do it through headphones. And say you play a pitch at, you want to hear a pitch at 1,000 hertz, it'll play in each ear a pitch that's maybe 10 hertz off. Let's say 5 hertz off. So we'll play one pitch at 995 and one at 1,005. And those two pitches are so close that your brain interpolates the average of the two pitches. So your brain will hear 1,000 hertz, but on top of that, you'll hear like this 10 hertz beat.
Yeah. So it's actually it looks like this. So if you have two frequencies that are slightly off of one another. So here I've got 4.5 kilohertz, so 4,500 hertz, and this one is at 4,000 hertz. So slightly different from one another. If you hear the two, you'll hear the difference in the pitch. It's very small, though. It's kind of a subtle thing. So one is a little bit higher than the other. So this one sounds a little bit higher than this one. And if you add them together and combine the two, so this is just a sum of these two waveforms. What you'll see is riding on top of that, you got a third, slower frequency. It sort of sounds like a beat. And so if you play this frequency to one ear, this frequency to the other ear, your brain, which sits in the middle of your two ears, hopefully, combines these two and interpolates this beat. And so you actually hear an auditory illusion, essentially. You hear this beat even though it's not present. So if you take off one headphone, take out one earbud, you hear the tone, take out the other, and no beat. You take out the other earbud, you hear a different tone, a lower tone, but no beat. Put them both in, you then hear a beat. So you hear this illusory beat that's not really there. So the idea is that you can set up this beat to be something that's biologically plausible. So something like 4 to 8 hertz, which is theta rhythm, and theta is related to all sorts of memory processes, for example. So if you're studying and you want to remember what you're studying, listen to these binaural beats that produce a beat in the theta range, and you'll remember everything. Right? Yeah, well, that's what these guys hope that is going to happen. This is what they hope to convince you of so that they can, sell you their product, basically. So this is a real webpage, idoser.com. I actually came across this because somebody from the Daily Universe called my colleague right next door, Scott Stephenson, who does addiction research. They wanted to know, is it possible to get high off of beats? Because that's really what these guys are claiming. So powerfully alter your mood, blah, blah, blah. But there's all sorts of things in the news that kids are getting high off of this, that it's changing their mood and it's producing this euphoric sort of high like drugs, drug-like high. And so they called the resident drug expert on campus, Scott Stephenson, who does addiction research, and he said, "What? No, that's stupid." Because it is stupid. It's not going to affect any of the stuff that he's interested in, the BTA, the nucleus accumbens, things like that. It's not going to do anything to that. It's not actually going to produce a high. It may make you feel dizzy and annoyed, which is what I get out of it. But you can go online. You can look up on YouTube binaural beats, put on your headphones, and listen to these soundtracks. And you can do that. We can't do it in here because it requires headphones. If I were just to play it over the speakers, you wouldn't hear anything. You'd hear two conflicting tones. It would be kind of obnoxious. But it's not really going to do that much. It may cause neural entrainment, though. So, like Josh was mentioning, you can get your neurons to fire in the same rate. I mean, that they have to in order for you to perceive the beat. Now, whether that's going to cause widespread differences in activation all across the brain, probably not. But nobody's taken this seriously enough to do any actual research on it. All right, so let's talk about your. Oh, sorry, Thomas.
Real quick, if you got that going fast enough, you induce a seizure, like with the flashing lights. Would you do that with?
So at flicker threshold.
Yeah, you do that with like tone.
I'm gonna guess no,
Okay.
just because we've spent how long? 6-7 weeks of the semester talking about vision, because our brains are very, very visual. So visual stimulus really drives activity in the brain. So that's part of the reason why you can induce a seizure with sort of flashing lights. We don't pay quite so much attention to auditory stimuli, so the activity from the auditory cortex is not as driving. Although it is in the temporal lobes, and if you've got temporal lobe epilepsy, then maybe. I'm going to guess no, but I can always be surprised. I mean, I could be wrong. That would be interesting, although I don't know how you would get that past IRB approval. I mean, you'd have to have a mouse model or something and try it out in rodents first. Ariel?
This is house, so it's not. But in Monday's episode, there was a blind guy, and they were trying, and he was having issues with his ears, like he heard sounds like really, really loud all of a sudden, and so they tried to induce a seizure with sound.
Did it work?
No, he fainted before they could actually get started. But so I mean, I don't know if that's even
How accurate house is even.
But
So
most of the time, their medical staff, they have medical staff on
do they really?
the. Yeah. Well, okay,
That makes it even worse.
so that they at least get the terms correct.
I can't watch House mostly because every patient gets an MRI, right? Because there's always something wrong with their head. And every patient crashes in the MRI, and they all run in with their stethoscopes and their badges and their keys in their pocket and everything. This is a huge magnet. This is a magnet that's 30,000 times the Earth's magnetic field. Their keys are going to go flying out of their pocket and stick to the side of the thing. They're probably going to hurt the patient on the way by. So, yeah, no, it doesn't work like that. And so just for that reason alone, I can't. Never mind all of the soap opera melodrama.
Notice the patient always crashed when one of the doctors is in the room.
Yeah.
Oh, it's not what we thought it was cut to commercial.
Right. Yeah. Yeah, it's pretty formulaic. So if we believe House, Thomas, maybe. Yeah. All right, so let's talk about your ears. How do we go from this physical stimulus in the environment to having a psychological, phenomenological experience of sound? So these are the structures that we're going to be talking about, and rather than me sort of fumble through these things and point at them, I found a pretty good video that demonstrates this stuff, and it's got Beethoven.
The sense of hearing is accomplished by a process known as auditory transduction. The ear converts sound waves in the air into electrical impulses, which can be interpreted by the brain. As sound enters the ear, it passes through the external auditory canal, where it meets the tympanic membrane. The tympanic membrane then vibrates in response to the sound. Sounds of a lower pitch, or frequency, produce a slower rate of vibration. And sounds of lower volume, or amplitude, produce a less dramatic vibration. Higher frequency sounds produce faster vibrations. The tympanic membrane is cone-shaped and articulates with a chain of 3 bones called the auditory ossicles. They consist of the malleus, the incus, and the stapes. The movements of the tympanic membrane vibrate the ossicles, passing on the information of frequency and amplitude. The 3 bones pivot together on an axis shown here in red. The pivotal axis is due to a series of ligaments which hold the bones in place within the middle ear cavity. The anterior malleal ligament and the posterior incutal ligament are of particular importance for the pivotal axis. Two structures which normally obscure this view of the middle ear have been removed. They are the chordae tympani nerve and the tendon of the tensor tympani muscle. Through the ossicles, the vibrations of the tympanic membrane are transferred to the footplate of the stapes. The stapes moves with a piston-like action, which sends vibrations into a structure called the bony labyrinth. The labyrinth is filled with a fluid called perilymph. If it were a completely closed and inflexible system, the movement of the stapes would be unable to displace the perilymph, and therefore unable to send vibrations into the bony structure. Due to the flexibility of a membrane called the round window, the stapes movement can displace the perilymph, allowing vibrations to enter the labyrinth. The corridor leading to the round window is found within the spiral portion of the bony labyrinth known as the cochlea. Vibrations produced by the stapes are drawn into the spiral system and return to meet the round window. The portion of the spiral passage in which vibrations ascend to the apex of the cochlea is called the scala vestibuli. The descending portion of the passage is called the scala tympani. A third structure, called the cochlear duct, is situated between the scala vestibuli and the scala tympani. The cochlear duct is filled with a fluid called endolymph, and when viewed in cross-section, the membranes separating the two fluid-filled systems are visible. They are Reissner's membrane and the basilar membrane. The membranes are flexible and move in response to the vibrations traveling up the scala vestibuli. The movements of the membranes then send vibrations back down to the scala tympani. A specialized structure called the organ of Corti is situated on the basilar membrane. As the basilar membrane vibrates, the organ of Corti is stimulated, which sends nerve impulses to the brain via the cochlear nerve. The actual nerve impulses are generated by specialized cells within the organ of Corti called hair cells. The hair cells are closely covered by a structure called the tectorial membrane. As the basilar membrane vibrates, the tiny clusters of hairs are bent against the tectorial membrane, triggering the hair cells to fire. The entire basilar membrane does not vibrate simultaneously. Instead, specific areas along the basilar membrane move variably in response to different frequencies of sound. Lower frequencies vibrate the basilar membrane closer to the apex of the cochlea, whereas higher frequencies produce vibrations closer to the base. This arrangement is known as tonotopic organization. Together, this sequence of events is responsible for our acoustic perception of the world around us.
So I like that video. Although it gets a little I've seen it. So let's talk about the parts. So let's talk about the outer ear first. So this is your pinna, the bit that you can see on the outside, the sort of funny shaped thing that holds your glasses up. Oh, it reminds me of a joke. Have I told you guys about Hungarian policeman jokes? They're hilarious. So they're sort of the blonde jokes of Hungary. So they don't make fun of blonde people, they make fun of policemen. So guy goes in, police cadet goes in for his sort of his detective's test. He wants to get a big promotion. And so they say, okay, the test is we're going to show you a photo, and we're going to show it to you for 2 seconds, and then we're going to take it away, and we want you to tell us everything that you can about the person in the photo after a delay. So this is going to test your perceptual skills. So they hold up the photo, 1, 2, put it away, and they say, okay, tell us about that person. That man has only 1 ear. Okay, anything else? Nope. That's the most distinguishing feature, is he only has 1 ear. Okay, we'll call you with the result of your test in a week. So he goes out, and the next guy comes in, do the exact same test. So they hold up the picture, take it away. The second guy says, that man has only 1 ear. All right, it's going to be harder than we thought. Thank you for coming. Don't let the door hit you on the way out. So he goes out, and as he's going out, the third guy is coming in, and he stops him and he says, dude, whatever you do, don't say that guy only has 1 ear, because that's what I said, and it's obviously wrong. I'm not going to get it. Good luck to you. So the third guy goes in. They hold up the picture for 2 seconds. They take it away, and the cadet says, that man's wearing contact lenses. It's amazing. How did you figure that out in 2 seconds? Well, it's obvious, isn't it? If he only has 1 ear, he can't wear glasses. All right, so this is what the guy was lacking, right? Is the other pinna. So the outer ear consists of the pinna, which helps with sound localization, and we'll talk about how that happens in a second, as well as the auditory canal. So this is the thing you're not supposed to stick anything into, including Q-tips, apparently, or pencils or sharp objects. So it's about 3 centimeters long. It's a tube-like structure. It protects the tympanic membrane at the end of the canal. The resonant frequency, interestingly, of the auditory canal is between 2,000 and 5,000 hertz. Remember where human speech is mostly, 2,000 to 5,000 hertz. Remember where we have maximum sensitivity, around 2,000 to 5,000 hertz. Kind of cool how that's set up. All right, so the middle ear is about a 2 cubic centimeter cavity separating the inner from the outer ear, as the names all imply, which is kind of handy. It contains the 3 ossicles, so the 3 smallest bones in your body, the malleus, the hammer, the incus, and the stapes, or the sternum. So the malleus moves due to the vibration of the tympanic membrane. It's the closest to the tympanic membrane. It affects the incus, which transmits the vibrations of the malleus to the stapes, which, as you saw in the video, moves back and forth the oval window. Did you have a comment, or you just stretching?
We were looking at the ear video, and I was thinking about like cochlear implants, how they actually stick. It's like a receptor up into the cochlea, right? Mm-hmm. So I was just trying to process that. I guess that's what does the actual processing of the signal into an electrical impulse rather than the structure of the inner ear, and then transmits that
right to your brain. Yeah, so if you have a problem with the ossicles, for example, say you're missing the malleus, then the vibrations are not going to get from the tympanic membrane to the oval window. So you're not going to get any vibrations going on, so you're not going to get any transduction going on. So yeah, I've actually got a slide later on about cochlear implants, but the basic idea is that you've got this spiral structure in the cochlea, and the implant is an electrode that goes around the spiral structure and activates or excites different locations on this. And it requires the cochlear nerve to still be intact. So you still take these impulses from the cochlea and transmit those to the brain.
That's when the sound's not getting to the cochlea. The vibrations aren't getting to the cochlea.
Right, exactly. Okay. Yeah, so you're not getting the transduction going on. So it could be a problem with this. It could be a problem with the transduction. A number of things could go wrong in this. And you're sort of skipping all of that and getting to the end of activating those neurons.
Stimulating the nerves yourself.
Right, exactly. Yeah. Yeah, and it's there's some controversy about cochlear implants. We can talk about that a little bit later after we sort of set up what all is going on here. One of the things that I find interesting in that video is remember the ossicles are rotating on that imaginary axis, right? So they're rotating in response to the vibration of the tympanic membrane. And he mentioned that there are two structures that he took out so that you could see it. One of them was the chorda tympani nerve, and the other one was the tendon of the tympanic tensor muscle. Tensor tympani muscle. What does that do? Why do you have a muscle connected to your tympanic membrane? I know you know.
Oh, wait. Is it so your ears pop when pressure changes?
No. So that's your eustachian tube, right? So that's just equalizing the pressure between your inner ear and your nasal cavity, basically. Any ideas? Does anybody have their textbook? Can I borrow it? Mind if I need it? So was that unexpected? Do you guys in the front not expect that coming up? So if you saw, thanks. Sorry to use your textbook. All right, so if you're expecting that, what do? You tense up, and you tense up this muscle in particular. So it attenuates the action of your ossicles, basically, so that your tympanic membrane isn't vibrating as much. And so you can have loud sounds like that are not quite as loud. So have you ever gotten into your car in the morning and turned on the key and the radio is just blaring? You can't believe that you ever listened to the radio that loudly. Yes? So this has happened to more people than just me? So why does that happen? Well, because you adjust to these things. You sort of expect these things to happen, and so you sort of you attenuate to these things. And part of the attenuation is this muscle action in your inner ear.
So if the muscle, or if you don't know it's coming, then the muscle doesn't tense up and that thing vibrates more?
Mm-hmm.
Is that okay?
Yeah, that's the idea. Thomas?
It's also so that when you speak, you don't go deaf.
Right. So
because when you're speaking, if your tensor tympani didn't contract, your tympanic membrane would vibrate a lot more than it does, and you would hear. It would be like you were yelling at yourself.
Right. So, yeah, because your voice is pretty darn loud right there. It's gonna vibrate quite a lot. Yeah.
Is that why we don't sound like what we sound like to ourselves?
That's part of it. Part of it is also that the vibrations are being transmitted, through your head to your ears instead of through the air medium to your ears. And so, if it's transmitted differently, then you're going to have a different sound spectrum, basically. All right. So this is a cartoon version of what's going on in the inner ear. You've got your tympanic membrane, your eardrum. You've got the malleus, the incus, and the stapes, or the hammer, the anvil, and the stirrup. So stirrup, this one, the name is kind of obvious what it is. Hammer and anvil, the functions imply the hammer hitting the anvil. Any mnemonics for remembering which one is the malleus and which one is the incus?
The M1 attaches to the membrane.
Okay, M for membrane, M for malleus. Does anybody know what the word malleable means? You can sort of change it. So if you have a metal that's malleable, you can hammer it out. So that this root is actually the same of hammer and malleable. That's how I remember it, but I'm sort of a geek. All right, and then where the magic happens. In the inner ear. So the main structure that we're going to talk about is the cochlea. We could talk about the bony labyrinth, which is the other part. That's part of the vestibular system. So we're going to ignore that, I think, pretty much permanently, and talk about the cochlea instead. So the cochlea is where auditory transduction is happening. It's the snail-shaped structure, the spiral-shaped structure. Filled with fluid, as we saw in the video, set into vibration by the stapes. So it's divided into the scala vestibuli and the scala tympani by the cochlear partition. The cochlear partition extends from the base, which is the stapes end where stuff is coming in, the vibrations are coming in, to the apex, which is at the very top. And the organ of Corti is contained within the cochlear partition. So that's where the transduction is actually happening, is in the organ of Corti. So you've got several things going on here. So one interesting thing is that the outer ear and the middle ear are filled with air. So this is why you have to pop your ears in order for them to work properly, because middle ear is filled with air, and so you want the air pressure between the outer ear and the middle ear to be about the same. The inner ear, though, is filled with fluid. So fluid is more dense. It takes more to transmit vibrations through this. So pressure changes in air transmit poorly in the denser medium. So if you ever go swimming, loud at the pool, and then you go under the water and it's pretty quiet, it's because the vibrations don't transmit quite as readily through the water, and so you have to amplify them. And that's part of what the ossicles are doing, is actually amplifying those vibrations, and in order to send those vibrations up into the cochlea. So this is sort of a partially unrolled cochlea, and this is if you were to take the cochlea, how it's all sort of scrunched up there, all rolled up, and you unroll it like a cinnamon roll, which is the only way to eat cinnamon rolls, right? And you can take a look at it. So this is the base here. The base end is next to the stapes, and then the apex is at the top. So the organ of Corti contains the basilar membrane, the inner and the outer hair cells, which are the actual receptors for hearing. So they're analogous to our photoreceptors in vision. So here it's these cells that are doing the transduction. They're taking this physical stimulus in the world and they're transducing it. So the physical vibrations, transducing those to neural signals. So basilar membrane, inner and outer hair cells, and then the tectorial membrane, which extends over the hair cells. Transduction at the hair cells takes place due to the interaction of these structures. So due to the relative movement of the tectorial membrane on top of the hair cells, here, this is a better example. So basilar membrane moves up and down. Tectorial membrane, in response to that, moves side to side. So as one moves up, the other one sort of moves off to the side, like this, I think. And the cilia on top of the hair cells get stretched out, basically. So they move side to side. Do I have a better picture of hair cells? Yeah, I've got better pictures of hair cells coming up. So this is the organ of Corti. This is the bit where the transduction happens. So previously we would talk about the retina and what's going on in the retina and the different layers of the retina. Here it's the basilar membrane that we care about, and the cochlea is analogous to the retina. Justin?
So I'm imagining it takes a different amount of time for transduction to go through auditory signals than from visual signals. So when you see somebody speak, but you hear it as their mouth moves, is your brain matching that artificially, or how does that?
Somewhat. So part of the delay is that sound travels slower than light, right? So you see things before you hear them. So things that happen way off in the distance, that's sort of taken for granted, right? So you see the lightning before you hear the thunder. If you have a mismatch between the two, say you're watching a video and the sound is not quite synced up to the video, if the video is slightly faster than the sound, you don't necessarily notice. Because that's usually the case, right? That you see things, you see someone's mouth moving before you actually hear the sounds coming out of their mouth, just because of the way the different media travel. If it's the other way, though, then it's really weird. Then you really notice. So even the same delay. So if you have, maybe a 50 millisecond delay between the video and the sound, if the video is first, you don't necessarily notice. But if you have the delay going the opposite direction, sound precedes video, then it's really noticeable, and then it kind of drives you crazy that these two things aren't synced. So you notice it more if the sound precedes. And it's not necessarily because transduction happens at different rates with these two things. So visual transduction and auditory transduction, I don't know the exact timing, but I think that they're pretty close to one another. So between the time that the auditory signal arrives and the signal arrives in your brain is not much different than when the visual signal arrives and the signal arrives in your brain.
So the biggest difference has got to be it's the distance traveled by the stimuli, right? Because you see the visual and the audio, they happen at the same instance. But like when you're in a soccer stadium and they kick the ball to the other side of the stadium, you see the ball kicked, and then there's a delay and you hear the sound.
Right.
From the distance, the sound waves actually travel slower.
Right, yeah. And your auditory system actually takes advantage of the relative slowness of sound waves. for example, in localizing sounds. So sounds are going to hit this ear. If they're coming from over here, they're going to hit this ear before they hit this ear, right? And that timing is important for telling you what direction things are coming from. So if you mess around with audio recordings, you can make it sound like, you know, something is moving from the left-hand side to the right-hand side of you know, whatever the auditory space is, just by messing with the timing of arrival in the different ears. We'll actually talk about some of the brain mechanisms for paying attention to differences in timing. That's just a picture of the same thing. This is a picture of the same thing, but it's scanning electron micrographs, which is pretty cool. So this is the tectorial membrane that's been peeled back so that you can see the hair cells here. So they're not really blue and pink like this. This has been colorized so that you can see how they line up like this. But this is, I think it's pretty amazing. Just looking at the cochlea, I'm amazed by the whole thing, by the whole structure of the thing. So yeah, so this is the scala tympani that's going back down to the base. This would up here would be the scala vestibuli, that opening there. And then this whole structure here is the organ of Corti, all collectively together. Anything else I want to say about that? No. All right, so how do we get different frequencies from this one structure, from the cochlea? So with vision, we get different colors from different kinds of photoreceptors, right? So the photoreceptors are sensitive to light of different wavelengths. Your hair cells, though, don't seem to be distinguished like that. So your hair cells aren't necessarily sensitive to sounds of different frequencies. It depends more on where they are in the cochlea. So the cochlea is sensitive to sounds of different frequencies, but the hair cells themselves are not necessarily. So there are two ways for nerve fibers to signal frequency. One way is for you to know which fibers are signaling. So where are the signals coming from on the cochlea? Another way to do it is to pay attention to how the fibers are firing. So in this case, you can look at the rate or the pattern of firing, and if the rate is at the frequency that you're interested in, well, then that tells you some information, right? So if you entrain the hair cells to fire at the same rate as your sound frequency, then that gives some information to the brain. Yeah, so this is basically the two situations. So here, these hair cells may be maximally sensitive to sounds at a given frequency, so you know that these ones are active and all the rest of them are less active. Or from all of the nerves coming from the cochlea, you know that these are firing at this rate, at this frequency, these are firing at a different frequency. So this is which cells are active, this is how the cells are active. Here I'm being a nerd. So the guy who figured out this sort of mapping of the cochlea is a guy named Békésy Georg, or Georg von Békésy. He was a Hungarian biophysicist, awarded the Nobel Prize in Physiology or Medicine for his research on the function of the cochlea. So what he did is he took cadavers and looked at their cochlea and figured out what is the response on the cochlea. How does the cochlea respond to different frequencies? And he figured out that the frequency of sound in the sound that you hear, so this is perceptual sound, is indicated by the place on the organ of Corti with the highest firing rate. So this is Békésy's place theory of hearing. So basically what matters is which part of the cochlea is active. So we figured this out in two ways. One is through direct observation of the basilar membrane in a cadaver. And the second was building a model of the cochlea using the physical properties of the basilar membrane. So he observed that the basilar membrane is thicker at the base and more wobbly at the apex. And it's also narrower at, more wobbly. So 3 to 4 times narrower, the other way around. So the base is 3 to 4 times narrower than the apex, and it's 100 times stiffer than the apex. So the apex is pretty wobbly and it's wide, and the base is pretty solid. So I guess next time we'll talk about what this means in terms of how it responds to different frequencies.